Okay, this is lecture 7 of our Computational Microelectronics course 2024. Due to my business trip to San Jose, I have to prepare the pre-recorded video. Thank you for your kind understanding. In this lecture, lecture 7, we will talk about one-dimensional nonlinear Poisson equation. In previous offerings of this course, usually this nonlinear Poisson equation was applied to the double gate MOSFET or double gate MOS capacitor or PN junction, but today we will make it even simpler. Okay, so let me just start from Poisson equation. Actually, in previous lecture, lecture 7, we have already discussed about the Poisson equation. So in that lecture, we considered the source-free version of Poisson equation. And when the net charge density vanishes, then here we have a vanishing source. In that case, we were able to discretize the left-hand side of our Poisson equation. Even the permittivity changes along the position coordinate. However, today we wanted to keep the net charge density. Now we have non-zero, possibly non-zero net charge density. Then what is actually this net charge density law? We have three different contributions for this quantity. So this net charge density law can be decomposed into three different components. One originated from hole density, and one originated from electron density, and finally the last one is coming from the doping density. So of course hole contribute positive Q to uh, net charge density, so we multiply positive Q, and also each electron contribute minus Q to net charge density, so we multiply minus Q. And of course, depending on the polarity, for example, donors will contribute positively, and ionized acceptors will contribute minus Q. However, in order to make it simple, we just introduced a unified form like positively referenced doping density. So that is positive for donors and negative for acceptors. Simply speaking, if we have p-type doping density 10 to the 17 per cubic centimeter. In this case, in this notation, we say that yes, doping density equal to just minus 10 to the 17 per cubic centimeter. This minus sign just to represent that this is a p-type doped region. Okay, so it's not that difficult to understand. So, of course, calculation of this law, especially from P concentration and concentration, that is the real problem of a TCAD simulation. So how many electrons are there, or how many holes are there? These questions are central questions of TCAD simulation. So in order to answer those questions, actually we need more sophisticated approaches. However, at equilibrium and only at equilibrium, then we can have special expressions for charge densities. At equilibrium, we are allowed to express our hole density and electron density in this way. So simply speaking, hole density is proportional to exponential of minus electrostatic potential. Also, electron density is proportional to the exponential of positive electrostatic potential. Of course, we have here normalization constant, and that is usually called as summer voltage. And by definition, this summer voltage is defined as summer energy divided by elementary charge Q. So you can see that actually this is corresponding to, also this is corresponding to the quantity like Vt and also Vt. Okay, for a while I will just use the full form of summer voltage. So by adopting these expressions, now we have the nonlinear Poisson equation. The term nonlinear comes from the nonlinear dependence of our equation on electrostatic potential. So that's the reason why we call it as a nonlinear Poisson equation. So please note that this form of Poisson equation is only valid at equilibrium condition, because hole density and electron density actually should be calculated by other means, but in this case under the assumption of equilibrium. So we have introduced special expressions strictly valid at only at equilibrium conditions. So although looks beautiful, but this is valid only at equilibrium condition. Please do not forget about the restriction or condition for this nonlinear Poisson equation. But anyway, now we wanted to solve this nonlinear Poisson equation. Then how can we do that? That will be our today's topic. So when we consider this nonlinear Poisson equation, so previously the terms like this one, the first one related with displacement vector, so that was already well discretized in our previous lecture. But now we have some terms like hole density, electron density, and position dependent doping density. So it is not that easy. Additionally, we have terms related with the integrated net charge density. So then how can we treat this one? So previously we have just analytically integrated the integral and eliminated the outermost derivative. But how can we do that? In this case, our approach or treatment is so simple. It means that, let's say, this is our position, and here we have x sub I, and of course here we have xi minus 1, and here we have xi plus 1. And now, using certain information like potential defined at x sub I position and potential defined at ix position, and also doping density defined at that position, what we can do is, well, at least the law at this x sub I position can be calculated. And our goal is to integrate this certain function. So we don't know how does it look like. It may look like this, or it may look like this, whatever. So that is quite much arbitrary. But at least we know the center value, and we wanted to integrate it over this range. So this point was from our notation. It was denoted as xi minus half position, and this position was denoted xi plus half position. So then how does it look like if we really perform the integration? Well, if we don't have any further information about the actual form of this low function, the net charge density, it will be almost impossible. However, simple treatment just says that, okay, we have the center value within this integration interval, so we will just multiply the distance. Then that will be the area underneath this rectangle, and that will be just treated as integration result. Of course, yes, for example, if we have really a steep increase of this function, then maybe, well, this um, rough or crude approximation will not be valid. However, we believe that anyhow, this integration, so centered at this integration domain, is more or less good approximation for our actual quantity. So please note that here, now you have the original functional form, and its a discretized form just looks like this. So what we have done is just to introduce the sampled values at x sub I and evaluate that function. Of course, by performing this one, we will get just rho evaluated at x sub I. Then we just multiply something. Something is the length of our integration domain. So that's it. So that was done in our simple approximation. Okay, so this expression will be used to construct the ith law of our B vector. So we will discuss this sentence once again. Um, so of course, in order to apply to the realistic case, we must consider, for example, MOS capacitor. So now we can consider oxide layer and also silicon layer. And of course, this entire system can be numerically analyzed. However, in this lecture 7, in order to make our life simple as possible, we will consider only silicon region. It means that our discussion now come back to that of lecture 4. In lecture 4, we just consider only silicon region, and after that, under the constant doping concentration, we have integrated the weighted multiplied Poisson equation and got certain analytic expression for surface electric field. So that was quite good, and we are now doing the same job with our numerical calculation. So in this case, we have two boundaries. Of course, this deep substrate And in this case, we just say that potential is given from our p-type acceptor doping density, and we will denote it as so phi infinity. And here, of course, we can introduce many different boundary conditions, but we let's say that we have the surface potential. What is the surface potential? The surface potential was defined as the potential at the interface referenced to the deep substrate. So it means that when we know this surface potential, then we automatically understand the value of our electrostatic potential at that x equal to 0 point. So now we will assume that our two boundaries, at our two boundaries, we know the electrostatic potential values. So that is our assumption. So then now let's go to the real implementation. Well, now, mm, now we have mm, n unknown variables because we have introduced n discrete grid points. So electrostatic potential evaluated at x naught and electrostatic potential evaluated at x1. All of those n unknown variables are there, and in order to find out their values, we need also n independent equations. Since variables are n multiples, so we have to also introduce n equations. Then how can we generate uh, n equations? We have two different or two methods to generate n equations. One is for for bulk node, except for the boundary nodes, we just perform uh, this evaluation of a nonlinear Poisson equation, and we can prepare n minus 2 equations. And finally, we just to evaluate boundary conditions at leftmost boundary and rightmost boundary. So by combining them all, then we will have eventually n unknown variables, and that exactly match it to the number of unknown variables. Well, now we have well-defined system, and we have some hope that we can solve this problem. But unfortunately, it is a nonlinear system because this is one of our unknown variable, and it has the exponential function, so it is no longer a simple linear relation. So we have nonlinear functions in it. So anyhow, we have to solve a set of nonlinear equations. So when nonlinear system is involved, then previously we have studied Newton method. So maybe you remember that one. However, peculiar point is now we have multiple variables, not just one variable. For example, we can have 100 variables or 200, sometimes 1,000, even larger. So we have so many variables, then how can we apply or how can we generalize our Newton-Raphson method? So please have a look at this line. So when we have only one variable, so we calculate the function which should be nullified eventually. Then in order to calculate the update of this unknown variable delta phi, we had to calculate the derivative of this function with respect to the unknown variable. So let me just generalize it a little bit further. So if we have two variables, for example, phi and psi, and let's assume that we have two different functions, so f and z. So what we wanted to do is just to find out a set of phi and psi which is satisfy f equal to 0 and g equal to 0. How can we find it? In order to find it, by applying the generalized version of the Newton method, we can easily understand maybe we have to calculate the partial derivatives of our functions with respect to unknown variables. But now we have two different functions and we have two different unknown variables. So the number of cases becomes 4. For example, round f over round phi, round f over round psi, round g over round phi, and round g over round psi. Okay, now we can calculate all of these 4 numbers. Then how can we arrange them and how can we use them to eventually calculate delta phi and delta psi? So since it is already covered in our previous lecture video, so in this pre-recorded lecture video, I will not repeat this same explanation. Instead, I strongly recommend you to watch my video. Its title is CM2020 L6.5. So although it contains more content, please start your watching from 26 minutes and 6 seconds. Then you will have this form. Okay, so maybe it will last about 20 minutes, so you have sufficient time to watch from this point to the till the end of the video. And the key lesson is when we have multiple variables and multiple equations, then we can consider many different partial derivatives, and by using those partial derivatives we must construct a matrix called as Jacobian matrix. So by constructing this Jacobian matrix and this residue vector, this is nothing but just the collection of our function values. Then now by solving this matrix equation, then we can get the x vector which contains all kinds of these delta quantities, the update for our unknown variables. Details can be found in this video, so I strongly recommend it to you. Carefully watch that video. So anyway, the details are hidden in that video, and now let me just show you some details, only important details. So let's consider the ith row of our A matrix, the Jacobian matrix. So in this case, of course, our I equal to 0 or I equal to n minus 1, these two rows were devoted to boundary conditions. So of course, in this case, you have to make a separate treatment. And let me just give you certain exposure to the most general cases. When we restrict ourselves to I value in between this range, then this is for our non-linear Poisson equation. Then when we have a nonlinear Poisson equation, then we can try to make a partial derivative with respect to certain values. For example, our equation itself is evaluated around x sub I. Then if we try to make a partial derivative with respect to x sub I plus 2, then that will give us identically 0. Why? It is because when you come back to the form of our nonlinear Poisson equation, the only dependencies found at those cases. So, yes, for example, this guy is unknown variable. This guy is unknown variable. Yes, yes, and also yes and yes. We have these unknown variables, and when we collect them all, we can identify they are shown as phi sub I plus 1 and phi I and phi I minus 1. So it means that when we consider a certain non-linear Poisson equation evaluated at nearby x sub I, that equation really depends on the quantities only neighboring, nearest neighbor point. So for example, phi I plus 2, this is already second nearest neighbor. However, we have no dependencies on those second nearest neighbors. Well, why we don't have such kind of dependencies? So it is because we have introduced a very simple, the lowest order discretization about our differential equation. Of course, if we consider even higher order discretization scheme, then eventually second nearest neighbor or third nearest neighbor can be involved. However, please, in our treatment, we will just apply the simplest one. So that's the reason why we don't have any dependencies on the second nearest neighbor or even further or the points far away from x sub I. So it means that what we have to do is just to consider the partial derivative with respect to x I plus 1 and with respect to xi and also with respect to xi minus 1. These three terms survive and all other terms does not appear at all. So that makes our consideration greatly simplified. So now let's consider these three components one by one. For example, if we consider this component of our A matrix, it means that equation is evaluated at x sub I and partial derivative with respect to the potential at phi xi plus 1 point. What is it? Yes, this quantity. Then please visit our discretized form here. Here we have 6 different circles. I already made it, and among them, which one is corresponding to the electrostatic potential evaluated at x sub I plus 1 point? You may find only one possibility here. So the partial derivative just gives us epsilon over delta x out of this calculation. So you will immediately have this expression. And let's go to another one. So this quantity is also we are considering same row. However, the column index is I minus 1. It means that we wanted to calculate the partial derivative with respect to phi sub I minus 1. Where can you find it? Then, of course, you can find it only at this point. Okay, so now you have a minus sign and minus sign. They are combined together to yield the positive sign. So our result is yes. Even in this case, we will have just epsilon over delta x. Now everybody understand the important one is diagonal component. Oh, sorry about that. So I made mistakes. So this is a diagonal component. And for this diagonal component, things becomes a little bit more complicated. Of course, the first two terms, yes, these two terms are coming from the spatial derivatives, yes, these and that. So it's not that difficult. However, all of our complication comes from this non-linearity shown in this row related term. We must do the partial derivative with respect to phi I component. So please have a look at this one. Here we have exponential minus phi over vt. Yes, and let's say this term is corresponding to exponential phi over vt. The difference is this guy is negative sign and this guy is positive sign. And when, of course, this one is indexed with i's and i's, then please try to evaluate this partial derivative. How does it look like? It just reproduce itself with a leading coefficient like 1 over vt minus. Also, when you take the partial derivative, also it represent so reproduce itself, and here we have a leading coefficient 1 over vt. Of course, difference is here we have a minus sign and positive sign. Well, anyway, although it shows a severe non-linearity, but anyway, analytically, it can be the derivative. We can take the derivative with respect to phi sub I. So then when we do it correctly, then we can find this form and hole density, and this form and electron density. Of course, previously we had doping density as a form of uh, doping. However, this one is a given constant at a given position. So when we take the partial derivative, it's gone. So we don't have any surviving term from our doping concentration. So now for arbitrary I values in this range, now you can calculate each component. So let me just fill out our A matrix, the Jacobian matrix. For example, if we consider, for example, this line, then of course it will have its diagonal component. Yes, diagonal component can be calculated in this way. And we have I plus 1. So using this one, we can feel this point. And also using this expression, yes, we can feel this point. Yes, let's say that, for example, this is I equal to 1. Then when we go to the next point, I equal to 2, then in this case, our center or diagonal point comes here, and this part is also taken from our diagonal component, and two surrounding parts are calculated from this guy and that guy. We can fill these non-zero elements one by one till the end of this procedure. Yes, we will fill many of them, almost all of them, and finally here we have a component corresponding to 1 and components corresponding to 1 because our, for example, our phi at 0 should be, for example, our phi surface potential and phi infinity should be 0. This is the function we have to evaluate at this I equal to 0 point. So when we take a partial derivative with respect to the first one, yes, it will give us just a number 1.0, diagonal component 1.0, and all other, yes, they will disappear. Following the same manner, we will have 1.0 at this last diagonal component and nothing in here. Okay, so I hope that this can give you some feelings about how can you fill out the Jacobian matrix. Okay, so now I assume that you can build AX equal to B system using function values and partial derivatives, and by using certain mathematical library. So now you can calculate this x, the solution corresponding to the update of your electrostatic potential. When you obtain this x, this is nothing but a collection of delta phi values at different positions like x0, x1, blah blah, up to xn minus 1. So then, just like a Newton method, we can keep this iteration. However, when we must stop, or when can we stop? So when every entry of this vector becomes sufficiently small. Uh, what is the meaning of sufficiently small? There is no uh, well-defined definition about this sufficiently small, but as a rule of thumb, for example, smaller than 10 to the minus 5 volt, or 10 to the minus 7 volt, or 10 to the minus 10 volt. Any of them can be a good criterion to stop your Newton-Raphson iteration. Okay, so for example, this one just shows one of my simulation result, and at the very first iterations, the increment or change of our electrostatic potential was more or less close to 1.0. Yes, in this case, we have a significant change of electrostatic potential, so we must go on. And how about the second, third, fourth? Yes, the error is reducing and the change of our electrostatic potential is getting smaller and smaller. However, still orders of 10 to the minus 2 volt, so means that several 10 micro, oh sorry about that, several 10 millivolt. This is far too high. However, if we go to in this range, so what does it mean? this range is corresponding to the microvolt, and this range is corresponding to the nanovolt, and this below this one is corresponding to picovolt or femtovolt. So yes, if our correction is smaller than 1 picovolt, then maybe we are quite much happy with this numerical solution. So we may stop here and say that this is a good enough numerical solution for our purpose. So that is quite typical for our calculation. So please do your exercise to get some feelings about when you have to stop or when you may stop. Okay, so now let's go to the real example. For example, flat band condition. Flat band condition means the surface potential equal to 0. And let's assume that p-type doping concentration is just 10 to the 17 per cubic centimeter. And in this example, I use just delta x as 1 nanometer and number of points is 201. So simply speaking, I say that this is 200 nanometer thick silicon structure. And at the end of this point, now we have a contact. So maybe you think that, oh, 200 nanometer, is this sufficiently thick or not? So why we don't make it, for example, 1 meter or 1 kilometer? It is simply because we cannot afford it, and we don't have to do that because all kinds of meaningful physical behavior will occur around within 100 nanometer or slightly uh, longer. So our selection for 200 nanometer is sufficiently good to describe this entire system. But how can I know that 200 nanometer is sufficiently wide or long? Mm, that is obtained from my experience and just to rule of thumb. For example, in this case, I can perform such a kind of a depletion approximation to estimate the depletion width. And in this case, depletion width is around 100 nanometer. So I can say if I set the simulation domain as 200 uh, nanometer thick, then every physical phenomena can be confined within this depletion region. So maybe I'm quite much safe to get sufficiently reasonable data. Of course, that need experience. So you must do your own experience to avoid misuse of your numerical technique. Well, anyway, in this flat band condition, so as expected, so this is a deep substrate, and this is the interface between oxide and silicon. In this case, band is flat, so electron density is also flat. But it's not of our interest. We wanted to increase the surface potential further and further and increase also electron density further and further. Then how can we do that? Oh, sorry about that. In this case, usually that simulation is called as a bias lamping, and usually when we say bias lamping, that is really meaning that the increasing the bias voltage, like gate voltage or drain voltage. But in this special example for lecture 7, I intentionally introduce a different value for our lamping or our boundary values. So length of, in this case, a length of the surface potential phi sub s. Then, of course, we can repeat this one. For example, it is easy to get the solution for phi s equal to 0.0 volt. Once after you get that solution, then increase its value to, for example, 0.1 volt. Then try once again get the solution by using the potential profile at this point as the initial guess. Since this voltage difference is not that high, maybe you can get the solution. And using these steps, then you can, for example, arrive 0.9 volt or 1.0 volt of your surface potential, please. And one note is, although I'm using here bias, so this bias is usually used the terms for terminal voltages or terminal currents. So my selection for boundary condition, surface potential, that is quite special only for this problem. So don't misuse this bias, misunderstand this term of bias. Okay. So anyway, when you go to the case of a surface potential corresponding to 0.9 volt, so it means that we have already a good strong inversion, and this figure just shows electron density. Yes, so n of x, and this is position x. As you can see, this is once again deep substrate, and even in this case, no electron density is constant here, and we have nothing special around this deep substrate. So our selection is good enough. For example, if we extend it to 300 nanometer, yes, we will have the same profile, and it does not change the solution in here. However, instead of that, I intentionally reduce the simulation domain to 100 nanometer thick in order to, for example, save the computational cost. So then what will happen? Since we have a little change in our numerical solution, so that will make certain distortion in your solution in this important part. Even more, if we reduce to 50 nanometer, then yes, there will be also more influence on your numerical solution. So rule of thumb is you have to introduce wide enough or large enough simulation domain to keep the correct physical solution. Okay. However, once you have enough large domain, then extending it further does not give you any advantages. So please try to make appropriate simulation domain for your own purpose. Okay. So as you can see here, the electron density at the surface point is quite high, like it is 1.5 times 10 to the 18 per cubic centimeter. Okay, so although Na is just 10 to the 17 per cubic centimeter, it means that at this deep substrate we have a hole density which is corresponding to 10 to the 17 per cubic centimeter. But now in this position, although this is a p-type material, but now we have 1.5 times 10 to the 18 per cubic centimeter electron density, not hole density. So certainly this can be found in n-type semiconductor, not p-type semiconductor. So that's the reason why we call it as a strong inversion. Okay, so now we have an inversion charge, and when we make the numerical calculation or numerical integration all over this one, of course, this is drawn in a semi-logarithmic scale, but of course we have to do it in a linear scale. Then we can calculate integrate electron density, and in this case it is corresponding to 2.3 times 10 to the 11 per square centimeter, because we have already made the integration along x direction. Previously that was per cubic centimeter, but it is now per square centimeter. So you can do it by yourself. Okay, so now you have your homework number 7, and once again the due date is quite far from the lecture day, because the national holidays in South Korea. So now we have two methods to calculate semiconductor charges in the silicon region of a MOS structure. One is an analytic expression studied in lecture 4, and the other one is the one we studied in today's lecture. So please make a comparison. So since we have already um, shown some result for 10 to the 17, so in this homework problem, so we wanted to slightly change the values. Now the p-type doping concentration is 4 times 10 to the 17 per cubic centimeter. So in this case, please try to analyze the same system with your analytic expression and your numerical expression. If you do it properly, then you will get wonderful agreement between these two cases. In this case, in this specific example with uniform doping concentration, which one is most clear? Of course, in this case, analytic solution is available, and your numerical solution should perfectly match it to the analytic solution, because in this case analytic solution is available. Okay, so thank you for your attention, and up to now, up to this lecture 7, we have covered how can we solve nonlinear Poisson equation in a simplified system. The part of a MOS capacitor only containing this silicon region. So of course, extension to the entire MOS capacitor can be possible. However, before talking about that interesting and important concept, for why after after some weeks after some weeks we will make another topic. We will discuss another topic related with neural networks. Okay, that will be quite new to this course, but I think that since nowadays many researchers are interested with application of neural networks into the semiconductor device modeling and simulation, so I think that it is a good chance for us to talk about that important topic. Okay, thank you and see you later.